Why does light, of all things, travel at one fixed speed, never faster, never slower? You can push a rocket harder and it moves quicker, but no matter what, light always races through the vacuum at the same pace. This isn't just a quirk of nature, it's a clue to something far deeper. The speed of light isn't merely about light itself, it's about how the universe is built. So, if you want to know everything about it, then watch this video till the end and subscribe to the channel. Let's begin. When we look beyond the mystery of why light moves the way it does, the first thing we need to understand is what we know about it. The simple, undeniable fact that light always travels at exactly 299,792,458 meters per second in a vacuum. That number isn't just an experimental finding or a figure scribbled down after years of lab work. It's something much more profound. It is, quite literally, a fundamental constant of the universe, an immutable truth that defines the behavior of space and time themselves. You could say it's one of the universe's few unbreakable promises. In the world of physics, constants are like the pillars that hold everything else up. They aren't values we expect to change. They're the rules that everything else must obey. The speed of light, represented by the letter c, sits at the top of that hierarchy. It's not just another measurement like the boiling point of water or the density of gold. It's a foundational value that every other physical law must respect. When scientists describe the equations that govern the universe, from the motion of planets to the energy inside atoms, C quietly sits within them, linking energy, mass, and even the flow of time into one coherent structure. To understand how special that is, imagine trying to build a clock that works anywhere in the universe. You'd need something so constant that no matter where you are, near a black hole, in the emptiness of interstellar space, or right here on Earth, the same laws of motion and time would hold true. Light provides that constant. Its speed is woven into the very way time and distance are defined. In fact, the meter, our unit of length, is no longer something we measure with a ruler or a metal bar. Since 1983, it has been officially defined by how far light travels in 1 divided by 299,792,458 seconds. That means the speed of light isn't measured by us. Instead, we measure everything else by it. When you hold a flashlight and shine it into the night sky, those photons aren't just moving fast. They're moving at the only speed allowed by nature for massless things. Whether you're standing still, running after the beam, or flying through space at incredible velocity, the light always moves away from you at the exact same rate. There's something deeply poetic about that, an absolute consistency that stands against the chaos of the cosmos. It's a reminder that amid the shifting forces of gravity and motion, there's still a constant rhythm to everything, an unwavering beat that synchronizes the universe. But here's where the wonder deepens. This fixed speed isn't just about light. It's about the structure of the universe itself. Light's speed is the cosmic limit that defines how information, energy, and even cause and effect can move through reality. The number isn't arbitrary. It arises from the fundamental properties of space and time. You could change the universe's mass, energy, or temperature, but as long as it remains this universe, built from the same space-time fabric we inhabit, C will remain the same. It's like the tension in the strings of reality, setting the tempo for every vibration, wave, and particle within it. This means when we say the speed of light, we're not just talking about photons darting through the vacuum. We're talking about a built-in property of the vacuum itself. The emptiness of space isn't really empty. It's a field of underlying energy, a stage whose structure decides what's possible. Light, being an electromagnetic wave, simply expresses that structure. It doesn't choose to move at c, It must. The fabric of space gives it no other option. And that's why this speed never changes. Because what's really fixed isn't the light, but the geometry of reality it travels through. Physicists discovered long ago that if you tweak the equations of electromagnetism, the number c pops out naturally, not as something that has to be set by hand, but as a consequence of the universe's physical constants. It's not just a speed, it's a signature, a fingerprint of how space and time communicate. And that leads us to something remarkable. This constant is so important that even things not directly related to light still depend on it. Einstein's famous equation, E equals mc squared, tells us that energy and mass are interchangeable, and that their relationship is governed by c squared. In other words, the speed of light connects the amount of energy stored in matter to the energy that could be released from it. It's the conversion factor that keeps everything balanced, from nuclear fusion in the sun to the tiniest processes inside an atom. Every time you turn on your GPS or send a message through the internet, the technology behind it depends on knowing that c doesn't vary. The satellites orbiting Earth account for time differences caused by relativity, differences that only make sense if the speed of light remains constant in all frames of reference. Even the way your phone locates you on a map relies on signals that travel at light speed. One fraction of a microsecond of error could mean the difference between your location being right or being hundreds of meters off. So when we say light moves at 299,792,458 meters per second, we're really describing the pulse of the universe. It's the pace at which reality updates itself, the ultimate clock that determines how cause becomes effect. This number defines not just how light moves, but how time flows and how distances make sense. Without it, the entire framework of physics, from relativity to electromagnetism to quantum mechanics, would collapse. But that leads us to a fascinating realization. If c is everywhere, shaping every equation and setting the rules of the cosmos, what does that really mean? Why is this number the maximum speed for everything? The fastest that energy, matter, or even information can move? What makes it the limit, the cosmic ceiling beyond which nothing can pass? To understand that, we have to look deeper into the meaning of speed itself and into the way space and time are woven together. Because light's speed isn't just fast, it's the maximum speed anything can ever have. And to grasp why, we must first understand what it means to call it the universe's speed limit. The speed of light, that elegant constant we call c, isn't just a curious number tucked away in textbooks. It's the quiet pulse beating through every corner of physics. It shows up everywhere, connecting theories that seem completely different on the surface. The swirling dance of electric and magnetic fields, the bending of space-time, the fusion of stars, and even the ticking of your watch. It's as though nature has chosen this one universal speed as a kind of cosmic signature, a thread that weaves together the forces and phenomena that define existence itself. In the world of electromagnetism, c first appeared long before anyone truly understood what light was. James Clerk Maxwell, in the 1800s, brought together electricity and magnetism into one grand, unified theory. 4 elegant equations that described how electric and magnetic fields interact. When he worked through the math, something astonishing fell out of the equations. Waves of electromagnetic energy that must travel through empty space at a precise speed. And when Maxwell plugged in the known values for the electric permittivity and magnetic permeability of free space, the result matched the measured speed of light exactly. In that moment, light stopped being a mystery or a particle or a simple beam. It became a wave of pure electromagnetism, moving at c, the speed determined by the very structure of space itself. But c didn't stop there. It found a new home decades later in Einstein's work, not just as the speed of light, but as a fundamental part of the architecture of reality. In Einstein's special theory of relativity, published in 1905, he didn't treat c as a property of light, but as a universal constant built into the geometry of space-time. He realized that all observers, no matter how fast they move, will always measure the same value for c. That simple statement upended the centuries-old ideas of motion and time. Before Einstein, people believed that time was absolute, that clocks ticked the same everywhere, regardless of how you moved. But if the speed of light is the same for everyone, time itself can no longer be fixed. It must bend, stretch, and adjust to preserve c. That realization changed everything. It meant that space and time weren't separate entities, but two aspects of one continuous fabric, space-time. And at the heart of this fabric lies c, setting the conversion rate between distance and duration. In simple terms, c tells the universe how to translate meters into seconds, how to turn motion into time, and time into motion. You can't talk about time without indirectly invoking c, because every second that passes, every meter that exists, is measured relative to that cosmic constant. Einstein's other great discovery, the equivalence of energy and mass, captured in E equals mc squared, is another expression of c's central role. It shows that mass can be converted into energy and vice versa, with c squared acting as the conversion factor. The number is so enormous that even a small amount of mass holds a staggering amount of energy. That's why stars shine, why nuclear power works, and why the universe itself is powered by transformations of matter into light. Without c, there would be no relationship between energy and mass at all, no way to connect the weight of matter with the power of radiation. But c doesn't just appear in grand cosmic equations. It quietly governs the everyday world too. Every electronic signal, every radio wave, every photon emitted by your screen travels at or is bound by that same speed. When engineers design communication systems, GPS networks, or even fiber optic cables, they're effectively timing the flow of information in relation to c. The synchronization of satellites depends on how long light takes to travel from orbit to Earth. Even the precise definition of a second, the tick of atomic clocks, must account for the constancy of c, because time and distance are interlocked by it. Quantum mechanics, too, bends to its rule. In quantum field theory, particles exchange force-carrying quanta that can never transmit information faster than c. This ensures that cause always precedes effect, that the order of events in one place can't be undone by another happening faster than light away. C isn't just about movement, it's about maintaining the logical structure of the universe. It's the wall that separates what can influence what from what never can. Even in the vast emptiness between galaxies, C plays its role. It defines how far light travels in a year, what we call a light year, and therefore shapes our understanding of distance and time across the cosmos. When astronomers look at distant stars, the light that reaches them has been traveling for millions or even billions of years. That means we're not seeing those stars as they are, but as they were when the light first left them. The finite, constant speed of light literally defines our view of the universe's history. It's a built-in time machine, showing us the past written in starlight. This omnipresence of C gives it an almost mystical quality. It's not a variable you can adjust or a limit that some things approach by accident. It's the scaffolding upon which the laws of physics are built. Every theory that describes the universe must bow to it. It's as though nature chose this single speed as the stitching that holds reality together. And everything else, gravity, quantum mechanics, motion, energy, must work around it. But why should there be a limit at all? Why should there be one universal number that caps everything from light to information. This is where things take a profound turn, because c isn't just a measure of how fast something can move, it's the maximum speed that anything in the universe can ever reach. Nothing, not even the most powerful explosion or the most advanced spacecraft, can surpass it. That's not because light is somehow special or limited by its own nature. It's because of what c really represents, the absolute boundary of space-time itself. And that brings us to the next great insight, the concept of the universe's ultimate speed limit. To understand why c is not just fast, but final, we need to look deeper into the structure of space and time, to see why nothing, no particle or signal, can ever outpace light. When we say that light is fast, we're almost missing the point. It's not merely quick or even unimaginably swift. It's as fast as anything can possibly go. The speed of light, this constant we call c, is the ultimate speed limit of the universe. It's not just the top speed for photons or electromagnetic waves. It's the upper bound for everything that exists, from the smallest particle to the largest galaxy, from a pulse of light to a burst of information. You can add energy, you can push harder, you can build stronger engines or fire more powerful rockets, but you can never cross that boundary. It's the one universal rule that no amount of clever engineering, force, or energy can break. To really grasp this, it helps to shift our perspective. The speed of light isn't fast compared to other things. Other things are slow compared to it. It's not that light happens to move at 299,792,458 meters per second. It's that space and time themselves are built in such a way that this is the fastest anything can go. C defines the structure of motion, the way the universe allows energy and information to flow. It's not an arbitrary ceiling. It's the very architecture of reality saying, this far and no farther. This cosmic limit was one of the most shocking discoveries of the 20th century. Before Einstein, people believed that speeds were relative in a simple way. If you were moving at half the speed of light and you turned on a flashlight, you'd expect the beam to move away from you at half the normal speed of light. But that's not what nature allows. No matter how fast you're going, when you measure the speed of that light beam, you still get the same answer, c. This defies our everyday experience. It's as if the universe constantly recalibrates time and space to preserve that one speed. The faster you move, the slower your time ticks, and the shorter your distances become. Also that light always moves at the same pace, no matter your motion. That means c isn't just a speed. It's the foundation upon which space and time balance each other. It marks the absolute limit of how cause and effect can be connected. Imagine space-time as a kind of fabric, an interwoven grid that connects all events in the universe. When something happens, say a star explodes, the information about that explosion ripples outward through space-time, carried by light and other forms of radiation. Those ripples expand outward at c, defining the boundary between what can and cannot be affected by the explosion. Nothing inside the universe can travel faster than those ripples. To move faster than light would mean to leap outside that boundary, to cross from a region that can be influenced by one event into one that can't. That would shatter the order of cause and effect. Einstein's theory of relativity formalized this beautifully. He showed that the equations of the universe themselves break down if something tries to exceed c. As an object accelerates closer to light speed, its mass, or more precisely, its relativistic mass, effectively increases. It becomes harder and harder to accelerate it further. The energy you pour in doesn't translate into more speed in the usual sense. It starts going into increasing inertia instead. The object resists acceleration more and more strongly, as though space itself is pushing back. To reach the speed of light would require infinite energy, and infinite energy simply doesn't exist. The math, the physics, and even the logic of space-time all forbid it. Think about it like this. If the universe were a racetrack, c isn't just the finish line, it's the edge of the track itself. You can run faster and faster, but the track doesn't extend beyond that point. There's nowhere else to go. That's why light, being massless, doesn't need to accelerate to c. It's born moving at that speed. For light, there is no alternative, no slower or faster option. It simply travels at the one speed allowed by the laws of the cosmos. What's truly elegant about this speed limit is that it doesn't come from some external lawgiver dictating nothing may go faster than light. Instead, it emerges naturally from the equations that describe space and time. It's as if the universe designed itself to make sense only if there's a finite speed that connects every event to every other. Without that limit, everything would happen instantaneously everywhere, and concepts like distance, time, and sequence would cease to have meaning. If you could send signals infinitely fast, there would be no before or after, no cause and effect, only a chaotic soup of simultaneous events. The existence of C keeps the universe orderly. It creates the structure that allows events to unfold logically, one after another. Even gravity, the most fundamental force shaping the cosmos, obeys this rule. According to Einstein's general theory of relativity, changes in a gravitational field, like the movement of a planet or the collapse of a star, travel through space as gravitational waves, and those waves move at the speed of light. Nothing, not even the tug of gravity itself, can outpace c. The detection of gravitational waves in 2015 confirmed this prediction. Ripples in space-time travel at precisely the same cosmic limit as light, reinforcing that c truly governs everything, not just photons. There's another beautiful way to think about this. The speed of light is not simply how fast light moves. It's how fast causality moves. It's the upper speed at which one event can influence another. If you tried to go faster than c, you'd be stepping outside the web of cause and effect, a place where effects could precede their causes, where messages could be received before they were sent, and where time itself would lose direction. In such a world, paradoxes would abound. You could, in theory, prevent your own birth, destroy your past, or undo an event before it began. Nature, it seems, abhors that chaos, so it forbids faster-than-light travel not just as a practical constraint, but as a safeguard against the breakdown of logical order. And yet, the universe isn't cruel about it. It's precise, elegant, and fair. Every particle, every wave, every bit of information must play by the same rule. The light speed limit is universal, the same in every corner of the cosmos, from the edge of a black hole to the emptiness between galaxies. That universality gives the cosmos coherence. It ensures that physical laws are consistent everywhere, that no part of reality drifts out of sync with another. So when we call c the speed limit of the universe, we're not being metaphorical. It's quite literal. It's the limit encoded into the very geometry of existence. It's the measure of how space stretches and how time flows. The absolute ceiling that keeps the symphony of the universe in harmony. Light speed is the tempo of reality itself. But this understanding brings us to a deeper question, one that often causes confusion. If light has this cosmic privilege, if it's always moving at the fastest possible speed, does that mean light is somehow special, a unique traveler blessed with nature's ultimate engine? The truth is far more subtle and far more fascinating. Because the reason light moves at c isn't about the light itself at all. It's about the shape and structure of space-time and the rules it imposes on everything within it. When people first hear that light has a speed limit, it's easy to imagine that there's something special about light itself, as if it possesses a built-in engine, a cosmic turbocharger that propels it to its maximum speed, or perhaps a mysterious resistance that stops it from going faster. But that's not what's really happening. The truth is far more profound, and it has little to do with the nature of light and everything to do with the architecture of the universe. Light doesn't choose to move at its speed. It doesn't accelerate, decelerate, or obey an external throttle. It simply travels at c because the structure of space-time gives it no other choice. The constant speed of light is not a property of the photon. It's a property of reality itself. To understand this, we need to shift how we think about motion. In everyday life, we imagine speed as something determined by energy or force. If you push harder, you go faster. If there's friction, you slow down. But light exists in a realm where those intuitions don't apply. Light has no mass, and because of that, it doesn't experience acceleration or deceleration in the way massive objects do. It doesn't climb to its speed like a rocket breaking through the atmosphere. It's born moving at c because that's the only way something without mass can exist. If light were to move slower than c, it would have mass. If it were faster, it would become imaginary in a mathematical sense, breaking the equations of physics entirely. The deeper reason lies in how space and time themselves are connected. When Einstein formulated his theory of relativity, he showed that space and time aren't separate entities. They're fused into a single, four-dimensional continuum called spacetime. The geometry of this spacetime dictates how all things move through it. And within that geometry, c is not just a speed. It's a fundamental constant that describes the ratio between changes in space and changes in time. It's the slope of reality's fabric, the built-in relationship between how distances stretch and how seconds pass. So when we say light always travels at c, what we're really saying is that photons move along a special kind of path through space-time, a null path. For massive objects like you, me, or planets, motion through space-time involves both space and time. As we move through one, we move differently through the other. But light's journey is unique. Because it has no mass, it doesn't experience time in the same way. From the perspective of a photon, time doesn't pass at all. The moment it's emitted and the moment it's absorbed are, in its own frame, the same instant. That's why it doesn't need to accelerate. Its motion is not a process unfolding over time. It's a geometric inevitability built into the shape of space-time itself. This idea can feel alien because it runs so counter to human experience. We think of speed as something relative, something we can change by applying force. But at cosmic scales, motion isn't about engines or pushes. It's about the geometry of existence. The universe has built-in conversion rules. The faster something moves through space, the slower it moves through time. For something with mass, that trade-off always balances so that its total motion through space-time never exceeds c. But light, having no mass, gives up motion through time entirely, moving only through space. It's as if all its energy is poured into distance rather than duration. This is why saying light moves at c is a bit misleading. It's not that light is trying to reach that speed. It's that light is the expression of what that speed means. It's the living example of spacetime's geometry in action. The universe defines c as the ultimate link between space and time, and light is what happens when that link is realized perfectly, when energy exists without the burden of mass, traveling along the only possible path that such energy can take. Even more fascinating is that c appears in equations that have nothing directly to do with light. It's not just a measure of how fast electromagnetic waves move. It's the scaling factor that converts between units of space and time across all of physics. When we express Einstein's energy-mass relation, E equals mc squared, that c squared isn't about photons at all. It's about the deep connection between the geometry of space-time and the nature of energy itself. It tells us that mass and energy are two faces of the same coin, and that c² is the conversion rate between them. The same constant that dictates light's motion also dictates the structure of energy and matter. So if you could somehow change the structure of space-time, change the way distance and time relate, then the value of c would change too, and with it, the entire set of physical laws that define reality. But in our universe, those relationships are fixed. The speed of light is really the speed of space-time's causality. It's the fastest possible way for one point in the universe to influence another. It's how the universe enforces order, making sure that cause always precedes effect, that information can't arrive before it's sent, that reality unfolds in a logical sequence. This is why physicists say the limit isn't about light itself, it's about the stage it moves across. Space and time together create the rules that everything must obey. Light simply plays its part perfectly, tracing the tightest possible line through space-time, a line that defines the boundary between what can happen and what cannot. It's almost poetic, really. Light isn't the master of the limit, it's the messenger of it. It doesn't tell the universe how fast to move. The universe tells light what speed to take. And because that speed is encoded into the very geometry of existence, it's the same everywhere, for everyone, at every moment in time. Whether a photon was emitted from a dying star billions of years ago, or from your lamp this instant, it's governed by the same rule. A rule not of light's making, but of the space-time it illuminates. Understanding this clears up the misconception once and for all. The constancy of light's speed isn't a trait of light, it's the fingerprint of space-time itself. And that realization opens the door to a deeper question. What exactly is light? Because before we can explore how space and time shape its motion, we have to understand what it's made of. What kind of entity can move effortlessly through the universe at this cosmic limit? Light, for all its mystery and beauty, isn't some mystical fluid racing through the cosmos or a stream of tiny bullets shooting out from stars. At its essence, light is an electromagnetic wave, a self-sustaining ripple of energy created by the interplay between electric and magnetic fields. It doesn't need wires, particles of air, or even a medium to move through. It carries its own means of propagation. The simplest way to describe it is this. A changing electric field creates a magnetic field, and that changing magnetic field in turn creates a new electric field. Together, they chase each other through the emptiness of space, forming what we perceive as a beam of light. Imagine dropping a pebble into a pond. The waves that spread across the surface are ripples in the water, transferring energy outward. Light works in a similar way, except its pond isn't water. It's the electromagnetic field that fills all of space. But unlike water waves, light doesn't need a physical substance to carry it. Its oscillations are built into the very structure of the field itself, meaning it can travel through the perfect vacuum of interstellar space just as easily as it can through air or glass. The electric and magnetic fields that make up light are always perpendicular to each other, and both are perpendicular to the direction in which the light travels. If you could somehow freeze a light wave in motion, though that's impossible, you'd see a rhythmic pattern of peaks and valleys in the electric field, with a matching pattern in the magnetic field oriented at right angles. Together, they form a beautiful, interwoven dance, one field giving birth to the other in an endless, self-perpetuating cycle. That's why we call it an electromagnetic wave. What's astonishing is that light is just one small part of a much larger family, the electromagnetic spectrum. This spectrum stretches from the longest, slowest radio waves to the shortest, most energetic gamma rays. All of them, radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are made of the same thing, oscillating electric and magnetic fields moving through space at the speed of light. The only difference between them is wavelength and frequency. Longer wavelengths correspond to lower frequencies and lower energy, like radio waves, while shorter wavelengths mean higher frequencies and higher energy, like ultraviolet and gamma rays. Our eyes are sensitive to just a tiny window in that vast spectrum, what we call visible light. Everything we see, every color we experience, is just our brain's interpretation of different frequencies of electromagnetic radiation. Now, even though we call it a wave, light is also a bit of a trickster. It doesn't behave only like a wave. It also acts like a stream of discrete packets of energy called photons. Each photon carries a specific amount of energy determined by its frequency. The higher the frequency, the more energetic the photon. This dual nature of light, behaving as both a wave and a particle, is one of the most fascinating aspects of quantum physics. It's not that light switches between being a wave and being a particle. Rather, it's that neither description alone fully captures what it truly is. Light exists as a quantum object that can exhibit both kinds of behavior depending on how we observe it. When you think about it, this duality fits perfectly with its role as the universe's speed limit. A photon isn't a tiny ball racing through space. It's a quantized pulse of electromagnetic energy that always travels at c. It doesn't have mass, which is why it doesn't need to expend energy to maintain that speed. For light, motion at c isn't a challenge. It's its natural state of existence. If light ever moved slower, it would cease to be light. It would gain mass, stop oscillating freely, and lose the very property that makes it what it is. The electromagnetic nature of light also explains why it can interact with matter in so many ways. When light encounters atoms or molecules, its electric field can push or pull on the charged particles inside them, causing electrons to oscillate, jump between energy levels, or even escape their atoms entirely. That's what happens in the photoelectric effect, a phenomenon that helped Einstein prove that light carries energy in discrete quanta. The energy of a single photon can knock an electron free from a material if it's high enough, showing that light isn't just a continuous wave, but also a carrier of individual packets of power. Light's electromagnetic nature also ties directly to the reason its speed is what it is. When James Clerk Maxwell combined the laws of electricity and magnetism in the 19th century, he discovered that electromagnetic waves naturally emerge from those equations, and their speed depends only on two fundamental properties of space itself: the electric permittivity, epsilon0, and the magnetic permeability, mu0, of the vacuum. When he calculated the value of c from those constants, it matched the measured speed of light precisely. That was the eureka moment that revealed what light truly was. Not some mystical emission, but a natural consequence of how electric and magnetic fields interact. The universe, through Maxwell's equations, was telling us, the speed of light is not arbitrary. It's the inevitable result of the electromagnetic properties of empty space. And yet, even calling it empty space is misleading. What we think of as nothingness isn't really nothing. It has structure, an invisible framework that defines how electric and magnetic fields behave. That structure, in turn, determines how fast electromagnetic waves can propagate. Change the permittivity or permeability of a medium, and you change the effective speed of light within it. That's why light slows down when it passes through water or glass. It's not that the photons themselves are moving slower, but that they're being absorbed and re-emitted, interacting with atoms in a way that delays their overall progress. The fundamental speed limit c never changes. What changes is the path light takes through matter. Understanding light as an electromagnetic wave also helps us see why it's so central to physics. It's the perfect bridge between the forces that govern the universe. Electricity and magnetism were once thought to be separate phenomena, sparks and compasses, lightning and magnets, until Maxwell showed they were two faces of the same coin. Light is the embodiment of that unity, the purest possible expression of the electromagnetic force in motion. It's the visible signature of one of the four fundamental interactions that shape everything from atoms to galaxies. So when we talk about light, we're really talking about one of nature's most profound symphonies, a harmony between electric and magnetic fields, energy and geometry, matter and space-time. It's the rhythm of the universe itself, and the fact that it moves at sea is not a coincidence, but a reflection of the deep connection between fields, energy, and the structure of the cosmos. But Maxwell's discovery didn't just reveal what light is. It hinted at something much larger, that the constants defining its motion were tied to the nature of space itself. When he found that electromagnetic waves must move at a specific speed determined by the vacuum's properties, he unknowingly uncovered the first glimpse of spacetime's geometry, the same geometry that Einstein would later show defined c as the ultimate speed of the universe. When James Clerk Maxwell began to unify the strange and beautiful world of electricity and magnetism in the mid-19th century, he likely didn't realize he was about to uncover one of the deepest truths about the universe, the reason why light moves at the speed it does. Before Maxwell, electricity and magnetism were seen as separate phenomena. One dealt with charged particles, sparks, and lightning, the other with magnets and compasses. But Maxwell sensed a deeper connection. He believed these were not two distinct forces, but intertwined aspects of a single, elegant framework. And when he wove them together mathematically, the result was something extraordinary. Equations that didn't just describe electric and magnetic fields, but predicted the existence of waves that could move through empty space at a fixed, universal speed. Let's step back and unpack what that means in a simple, intuitive way. Imagine you have an electric field, the invisible influence that surrounds a charged particle, like the way a balloon's static charge can pull on your hair. Now imagine that electric field starts to change. Say, the charge moves or oscillates. Whenever an electric field changes, it automatically creates a magnetic field. Likewise, if a magnetic field changes, it creates an electric field. This mutual creation, each one giving rise to the other, forms a self-sustaining cycle. The result? A disturbance that can travel outward indefinitely, even through the vacuum of space, without needing anything material to carry it. That disturbance is an electromagnetic wave. Now, what Maxwell realized is that the properties of these waves, how fast they move, how they vibrate, depend entirely on the intrinsic nature of the vacuum itself. You see, space isn't truly empty. It has fundamental characteristics that define how electric and magnetic fields behave within it. The two key properties are called electric permittivity and magnetic permeability. The first measures how much resistance the vacuum offers when you try to form an electric field within it. In other words, how easily electric lines of force can spread through space. The second measures how well magnetic fields can form and interact in that same space. These two constants define the stiffness and responsiveness of the electromagnetic fabric of the universe. Maxwell discovered that if you combine these two constants, the vacuum's ability to sustain electric and magnetic fields, you can determine the speed at which electromagnetic waves must travel. And when he calculated that speed, it came out to be exactly the same as the measured speed of light. This wasn't a coincidence. It was a revelation. Light is an electromagnetic wave, a traveling oscillation of electric and magnetic fields woven together by the laws of nature. The speed of light isn't something arbitrary or chosen. It's dictated by the vacuum's very structure. The universe doesn't just allow light to move at that speed, it requires it. To put this into a physical analogy, think about waves on the surface of a pond. The speed of those water waves depends on the properties of the water, its density, its surface tension, and how easily it can be disturbed. Similarly, the speed of light depends on how the medium of space responds to electric and magnetic changes. Space, in this sense, behaves like a kind of invisible field medium, one that can vibrate electromagnetically, change its properties, and you would change the speed of light. But in our universe, those properties are fixed, giving us a cosmic constant that anchors everything. C, the speed of light in a vacuum. Maxwell's realization was nothing short of revolutionary. For the first time, humanity had a reason for light speed, not an empirical measurement, but a theoretical prediction that emerged naturally from the structure of the equations. Light moves at that exact pace because the vacuum has certain electromagnetic properties, and those properties can't be altered. This was a new kind of understanding, a bridge between theory and observation that tied together electricity, magnetism, and optics into one unified framework. But the consequences were even deeper than Maxwell could have imagined. His work implied that the speed of light wasn't just a number describing how fast a wave moves. It was a built-in feature of the universe, arising from its fundamental constants. This realization laid the groundwork for Einstein's theory of relativity decades later. When Einstein came along, he didn't have to assume the constancy of the speed of light as an experimental fact. Maxwell's theory had already shown that the value of c was woven into the structure of space itself. Einstein simply asked, what if that constancy isn't just true for light, but for all of physics? Think about what that means. Maxwell's equations describe how light propagates, but hidden within them is something far more profound. They reveal that the vacuum of space is not a passive void. It has measurable qualities that determine how quickly cause and effect can travel through it. Those qualities, the electric and magnetic properties of space, create a universal speed that acts as a ceiling for everything in existence. When you see a beam of sunlight stream through your window, you're not just looking at energy racing through emptiness. You're witnessing the natural vibration of the vacuum itself, moving exactly as fast as the laws of nature allow. The beauty of Maxwell's insight is how seamlessly it connects the invisible with the visible. From the motion of charges in a wire to the glow of distant galaxies, everything electromagnetic, every radio signal, every X-ray, every warm ray of sunlight, follows the same mathematical rhythm. The same constants of space determine the propagation of a radio broadcast from Earth as they do the journey of a photon emitted at the dawn of time. This universality is what makes c so sacred in physics. It's not just a number. It's the measure of how space and time respond to the presence of fields and energy. Maxwell's discovery transformed our understanding of light from something mystical into something mathematical. But in doing so, it also made it more wondrous. He showed that the speed of light isn't chosen by light itself, but by the very vacuum that hosts it. The dance between electric and magnetic fields is choreographed by the properties of the universe, and c is the tempo of that dance. A tempo so fundamental that everything else in physics must keep time with it. And yet, even this magnificent discovery was only the beginning. Maxwell revealed that light moves through space according to the electromagnetic nature of the vacuum. But Einstein would later reveal that the vacuum itself has a geometry, a curvature, a shape. Space and time, he showed, aren't static backdrops but dynamic entities intertwined into a single fabric. And that fabric enforces the constancy of c everywhere. Maxwell discovered the melody. Einstein uncovered the instrument on which it's played. So now that we understand how Maxwell's work predicted the speed of light, the next step is to explore what Einstein did with that knowledge. how he took this constant speed and reimagined space and time themselves around it, transforming physics forever. If the idea that the speed of light is determined by the very nature of space still feels abstract, there's a simple and surprisingly familiar way to think about it, through the analogy of waves on water. Imagine standing by a calm lake. You toss a stone into it, and ripples begin to spread outward across the surface. No matter how big or small the stone, those ripples always move at a certain speed. You can throw the stone gently or hurl it with all your strength. You'll create bigger or smaller waves, but the speed at which they travel across the surface doesn't depend on how hard you threw. It depends entirely on the properties of the water itself. The water's density and surface tension together determine how quickly those ripples can move. If you were to pour oil onto the water, you'd see the waves slow down, not because you changed how you threw the stone, but because you altered the medium's characteristics. Likewise, if the water were denser or more viscous, the ripples would take longer to spread. The waves are simply obeying the physical laws of their environment. They can't go any faster than the water's nature allows. Now, carry that idea into the cosmos. Light is also a wave, not a wave of water or air, but a wave of electric and magnetic fields that ripple through the structure of space itself. And just like those water ripples, the speed of light is determined by the properties of its medium. In this case, the electromagnetic characteristics of the vacuum. The vacuum of space, even though we call it empty, has measurable traits. Its electric permittivity, which governs how electric fields form, and its magnetic permeability, which determines how magnetic fields interact. These constants of nature define how light moves through the universe, just as water's surface tension and density define how ripples move through a pond. That's why Maxwell's equations predicted light's speed so perfectly. He wasn't describing light as an independent traveler with its own propulsion. He was describing the medium of space and how that medium responds to disturbances in its electromagnetic fields. Once you know the density and tension of that invisible fabric, you automatically know how fast those waves will move. And the number you get, roughly 300 million meters per second, isn't negotiable. It's written into the structure of reality itself. This analogy helps dispel one of the biggest misconceptions about light, that it somehow chooses to move at that speed, or that its energy determines how fast it goes. That's not true at all. A low-energy radio wave moves just as fast as a high-energy gamma ray. Their wavelengths and frequencies differ, their ripples are stretched or compressed, but their speed remains identical in a vacuum. It's not about the wave's intensity, it's about the medium's unchanging properties. To extend the analogy a little further, imagine again that pond. If you could somehow alter the water, make it thicker or more resistant, you'd change the speed of the waves. The same principle applies when light moves through materials like glass or water. Inside those substances, light seems to slow down. But this doesn't mean the photons themselves are actually moving slower between atoms. Instead, they're constantly being absorbed and re-emitted, bouncing between interactions with the particles in the medium. That series of microscopic delays makes the wavefront appear to move more slowly overall. The light's fundamental speed, the universal constant c, doesn't change. The medium just causes a kind of delay, a detour through its microscopic structure. The beauty of this analogy is that it reminds us how the speed of any wave is really a statement about the world it moves through. In a sense, every wave reveals something about its environment. Ocean waves reveal the sea's depth and density. Sound waves reveal the air's temperature and pressure. Light waves reveal the structure of space-time itself. They tell us how the vacuum behaves, how it stores and transmits energy, how it lets information flow, how it connects events across vast distances. Now here's where the analogy takes a leap from simple to cosmic. On Earth, the water in your pond or the air around you can be disturbed, heated, cooled, stirred, compressed, and that changes how waves move through it. But the vacuum of space, as far as we can tell, doesn't change. Its properties are uniform everywhere, from the center of our galaxy to the emptiest stretches between galaxies. That's why light speed is always the same, no matter where it travels or who measures it. The pond of spacetime has a perfectly even surface, no thicker here, no thinner there, and so the waves that move across it obey the same unyielding rhythm everywhere in the cosmos. When you watch sunlight glint off a lake, the analogy comes full circle. The ripples on the water's surface are visible because of the ripples in the electromagnetic field that we call light. One kind of wave reveals another. The gentle shimmer of reflected light is, in a sense, a dialogue between two different kinds of media, water and space, each with its own rules, each dictating how its waves can move. And both remind us that motion is never about the traveler, it's about the road beneath them. In the same way, light's constant speed is a direct reflection of the road it moves on, the structure of space-time itself. The universe isn't giving light special treatment, it's simply showing us that its geometry is consistent. Space and time set the pace, and light keeps perfect time with them. But this analogy also prepares us for the next great leap. Because when Einstein looked at this same problem, he realized something even deeper. That this universal speed isn't just a property of light or space, but of the very geometry that ties space and time together. The constancy of light's speed is a hint that space and time aren't separate fabrics at all, but two threads of one cosmic tapestry. And understanding that connection would change everything, not just how we see light, but how we understand motion, time, and the universe itself. When James Clerk Maxwell revealed that light's speed comes directly from the electromagnetic properties of the vacuum, it seemed like one of the most complete answers science could ever provide. Yet, as elegant as that discovery was, it raised a subtle but profound problem. If light's speed is fixed by the nature of space itself, what happens when the observer is in motion? What if you're chasing a beam of light? Would you see it moving slower, the way you might see a car's speed relative to your own? Or would its speed somehow remain unchanged? For decades, physicists struggled with this question. It didn't make sense that the speed of light could be constant for everyone, regardless of their motion. In everyday life, speeds are always relative. If you're running on a train moving at 50 kilometers per hour and you throw a ball forward at 10 kilometers per hour, someone standing on the ground would see that ball move at 60 kilometers per hour. That's how motion works in classical physics. So by that same logic, if you were traveling in a spaceship moving close to the speed of light and you turned on a flashlight, shouldn't the beam move away from you more slowly than it would for someone standing still? But no. Experiments kept proving otherwise. No matter how fast you were moving, if you measured the speed of light, you always got the same answer, roughly 300 million meters per second. No faster, no slower. The universe, it seemed, was enforcing an impossible rule, one that broke the intuitive way humans had always understood motion. Then, in 1905, Albert Einstein stepped forward and did something revolutionary. Instead of trying to force light's behavior to fit our old ideas of space and time, he redefined space and time themselves. He realized that the constancy of the speed of light wasn't a problem, it was a clue. A clue that the universe doesn't operate under separate, rigid ideas of distance and duration. Instead, those two concepts are interwoven into a single, flexible framework. Space-time. Einstein's insight was radical and beautiful in its simplicity. He said that the reason the speed of light is always the same for every observer isn't because light is special, it's because the geometry of space-time makes it so. Space and time aren't independent arenas where events unfold. They're interconnected dimensions of one deeper reality. And in that four-dimensional fabric, the speed of light, the constant c, is a built-in feature of the geometry itself. It's not a speed that something travels through space. It's a ratio that links how space and time stretch and contract relative to each other. Imagine space-time as an immense, elastic fabric. When you move through it, your motion isn't just across space, it's also through time. And the total motion you can have through both together is always limited by c. The faster you move through space, the slower your time flows. The slower you move through space, the faster your time flows. This trade-off keeps the overall balance constant. Light, having no mass, uses up all its motion moving through space, leaving none for time. Which is why, from light's own perspective, time doesn't pass at all. This idea that the speed of light defines the geometry of space-time changes everything about how we view the universe. It means that when you move faster, distances appear to contract and time appears to dilate. Not because anything physical is wrong with your clock or your ruler, but because space and time themselves bend and stretch to preserve the universal constant, c. This is the heart of Einstein's special theory of relativity, and this is where the world shifted. The constancy of c wasn't just a property of light anymore. It became the keystone of reality's architecture. It means there's no absolute frame of reference, no true rest or motion, only relationships between observers. Each observer experiences space and time differently depending on their motion, but the laws of physics and the speed of light remain identical for all. The universe doesn't care how fast you're going. It always plays by the same rules. To visualize this, think of space-time as a vast grid that stretches and flexes as things move. When you're standing still, your motion through time is steady, like moving straight up along the grid. But when you start traveling through space, say in a rocket, your path tilts. You're now moving through both space and time, and because the total motion through space-time is constant, your movement through time slows down as your spatial speed increases. No matter what you do, the slope of your trajectory through this grid can never be steeper than that defined by light. Light's path, the line that represents its journey through space-time, forms a perfect boundary, the steepest possible angle that still fits within reality. That's why the speed of light isn't just fast, it's fundamental. It's the limit set by the very shape of space-time. It marks the boundary between possible and impossible, between cause and effect. Everything that happens in the universe must occur within the region of space-time that light can reach from a given point, a region physicists call the light cone. Anything outside that cone is forever beyond influence. No signal, no interaction, no cause can cross that barrier without violating the order of time itself. Einstein didn't just solve the puzzle of light's speed. He revealed that it was never really about light at all. It was about how the universe knits together its two most fundamental quantities, space and time. What Maxwell had shown mathematically, Einstein translated into the geometry of existence. Light's constant speed isn't a mystery of motion. It's a statement about the very fabric of reality. This realization changed everything, not just our understanding of physics, but our understanding of reality itself. It told us that time is not universal, that simultaneity is an illusion, that energy and mass are interchangeable, and that the cosmos has an absolute rhythm woven into its structure. The constancy of light's speed is the law that unites all observers, all moments, and all places into a single, consistent universe. But Einstein didn't stop there. Once he saw that the speed of light defined space-time's geometry, he began to see something even deeper, that light's constant speed isn't just about how space and time behave, it's about how they exist together. And from that insight came one of the most profound concepts in all of physics: space-time itself. A unified stage where light, matter, and motion all play their roles in perfect balance. Here's where Einstein's insight becomes truly mind-bending, and yet profoundly elegant. He discovered that no matter how fast you move, no matter how hard you try to catch up to a beam of light, you will always measure it traveling at the exact same speed, roughly 300 million meters per second, or the cosmic constant, c. It doesn't matter whether you're standing still, soaring through space at half the speed of light, or even theoretically chasing a light beam at 99% of its speed. When you measure it, the answer will always come out the same. This defies every instinct we have about motion. In our everyday experience, speeds add and subtract in simple ways. If you're driving a car at 50 kilometers per hour and throw a ball forward at 10, someone on the sidewalk would see that ball moving at 60. It's common sense. The car's speed adds to the ball's. But light doesn't play by those rules. If you're traveling at half the speed of light and you shine a flashlight forward, you don't see that beam moving away from you at half speed. You still measure it at c. And an observer standing still, watching you fly by, also measures that same beam moving at c. Somehow, both measurements, yours and theirs, are right. To make that possible, the universe does something extraordinary. It adjusts the flow of time and the scale of space for each observer so that the speed of light remains the same for everyone. When you move faster, your clock slows down relative to someone who's standing still. Distances in the direction of motion shorten. And these two effects, time dilation and length contraction, perfectly compensate so that light's speed never changes. It's not that the light beam alters its behavior, it's that space and time themselves flex and bend to preserve the cosmic rule. Einstein realized that our traditional ideas of absolute time and space, the Newtonian notion that there's one true clock and one universal ruler, simply don't exist. Instead, each observer carries their own space-time framework. Your seconds and your meters are valid for you, but someone moving at a different speed will experience them differently. Their seconds might be longer, their meters shorter. Yet when either of you measures the speed of light, the differences cancel out, leaving that sacred constant untouched. This means that time itself isn't universal, it's personal. The faster you move, the more slowly time passes for you compared to someone at rest. Likewise, distances shrink in the direction of motion. These effects aren't illusions or quirks of measurement. They're built into the fabric of reality. They've been confirmed in countless experiments. Particles in accelerators live longer than they should because their time slows down. Atomic clocks flown around the world return slightly out of sync with those left on Earth. The universe bends space and time so that c remains constant, no matter what. To appreciate how strange this is, imagine a thought experiment. Picture yourself in a spaceship cruising through the cosmos at 99% of light speed. Outside your window, you see a distant star, and you decide to measure how long it takes light from that star to reach you. You perform the experiment, and, as always, you find the light traveling at c. But someone back on Earth, watching your ship zoom by, also measures that same light from the same star, and they too get c. Even though you're moving almost as fast as the light, there's no catching up, no slowing it down. The laws of physics hold perfectly for both of you, even though your experiences of space and time differ wildly. This is the heart of relativity. The laws of physics, including the speed of light, are the same for all observers, regardless of their motion. There is no preferred frame of reference, no universal stage on which everything unfolds. Each observer's reality is equally valid, and space-time itself adjusts to make sure that light's speed stays consistent across them all. Einstein didn't just declare this as a rule. He derived it from logic and the observed facts of nature. He asked a simple question: what must the universe look like if the speed of light is always the same? The answer led to a completely new geometry of space and time. Instead of being rigid and separate, they became flexible and unified, stretching and contracting to ensure that every observer agrees on one thing only: the value of c. What's remarkable is that this isn't just a trick of perception. The effects of relativity are real and measurable. If you move fast enough, time for you genuinely slows down relative to someone else. If you travel close to light speed to a distant star and return, you'll find that more time has passed for those who stayed behind than for you, a phenomenon known as the twin paradox. It's not a contradiction, but a direct consequence of space-time geometry. Even the concept of simultaneity, the idea that two events can happen at the same time, falls apart under relativity. Two observers moving relative to each other won't agree on whether events in different places occurred simultaneously. There's no universal now. Each observer's present is tied to their motion. The only thing all observers can agree on, the one thread connecting their distinct experiences, is the constancy of the speed of light. This insight reshaped everything. It showed that space and time are not separate stages upon which the universe acts, but are dynamic participants in the play themselves. The speed of light, c, is not just a limit, it's the rulebook that space and time follow. It defines how they interact, how they warp, and how they preserve order in the cosmos. What's truly humbling is how nature enforces this law so flawlessly. The universe doesn't need to adjust light speed to fit our perspective. Instead, it adjusts our experience of time and distance so that c remains universal. It's as though reality itself bends around that number, ensuring that it never wavers, no matter who's watching. And this constancy isn't just an abstract quirk. It's the foundation of causality, the principle that cause must precede effect. If different observers could measure different light speeds, the sequence of events could flip from one perspective to another. One observer might see an effect happen before its cause, unraveling the logical fabric of reality. But because c remains fixed for all observers, cause and effect are preserved. The universe maintains its internal consistency through this one elegant rule. So, when Einstein said that light speed is built into the geometry of space and time, he meant that c is the heartbeat of reality, the invariant quantity that holds everything together. It's not just a number in an equation, it's the foundation that makes measurement, motion, and meaning possible. No matter how fast we move, no matter how far we go, we are bound by that rhythm, the universal tempo that defines what it means to exist in space-time. But to truly appreciate what this constancy means, we need to understand what Einstein discovered next: that space and time aren't separate threads, but parts of a single cosmic fabric, and that c is the thread that weaves them together. Einstein's great leap wasn't just in showing that the speed of light stays constant, it was in realizing why. Space and time, he discovered, aren't two separate stages on which the universe performs. They are two sides of the same cosmic fabric, what we now call space-time. This was a profound shift in human understanding. Time isn't a universal clock ticking the same for everyone, and space isn't an unchanging grid stretching infinitely in all directions. Instead, they are woven together, and their relationship is defined by one fundamental constant: the speed of light, c. Think of c as the universe's built-in conversion factor between space and time. It tells you how much distance in space is equivalent to a duration in time. In a sense, c translates meters into seconds and seconds into meters, binding both into a single measurable reality. Because light always moves at that speed, it provides the perfect bridge between how far something travels and how long it takes. That's why, in physics, distance and time are never truly separate. They're expressed in the same units once multiplied or divided by c. This blending of space and time explains all the strange effects of relativity. When you move faster through space, you move slower through time. Both change in perfect proportion to one another, keeping the total motion through space-time constant. The geometry of the universe demands it. For light, which moves at c, all of that motion goes into space, none into time, which is why, from light's own perspective, time doesn't flow at all. In this unified view, the speed of light isn't just a number that limits how fast things can move. It's the fundamental ratio that defines how the universe itself is measured and experienced. C sets the scale of space-time, acting like the stitching that holds reality's dimensions together. Without it, space and time would unravel into separate, meaningless pieces. And once you see the world this way, it becomes possible to visualize how events unfold, not just as points in space or moments in time, but as coordinates in a four-dimensional continuum, connected by the constant rhythm of light speed. If you want to visualize what Einstein meant when he said space and time are linked, imagine the universe as a vast, invisible grid, a four-dimensional fabric made up of 3 dimensions of space and 1 of time, interwoven so tightly that you can't change one without affecting the other. This fabric is what physicists call spacetime, and it's the arena in which all of reality plays out, from the movement of galaxies to the ticking of your wristwatch. Everything that has ever happened or ever will happen takes place somewhere on that grid. Now, within this cosmic fabric, every object traces out its own path, a record of where it has been in space and when it was there in time. We call this path a world line. If you stand perfectly still, your world line is straight and vertical, representing the steady passage of time while you remain in one place in space. But if you start walking, your world line tilts. You're now moving through both space and time. The faster you move through space, the more your world line tilts away from the vertical, and the slower your time flows relative to someone standing still. At the extreme limit of this tilt lies the path of light, the most tilted line possible in space-time, one that forms a perfect boundary between what can and cannot happen. Because light moves at the universe's maximum speed, its world line makes a fixed angle through space-time, always the same, no matter where or when. This angle defines what physicists call the light cone, one of the most important concepts in all of modern physics. To picture it, imagine a single event in space-time. Say, you snapping your fingers right now. That snap creates a point on the space-time grid. It has a location, where you are, and a time, when it happens. Now draw all the possible directions that light could travel outward from that moment. Those paths spread out like a cone, the future light cone, representing everything in the universe that your snap could possibly influence. No sound wave, no signal, no object, not even gravity itself can move faster than light, so nothing outside that cone can ever be affected by what you just did. The edges of that cone mark the absolute limit of cause and effect. There's also a second cone pointing backward in time, the past light cone. It includes every event that could have influenced your snap, the photons bouncing off the walls that you saw a moment ago, the neurons firing in your brain that told your hand to move, even the ancient starlight that reached Earth long before you were born. Everything outside that cone, events too far away or too early to have reached you at light speed, can never have influenced your action in any way. Together, these two cones, one pointing forward, one backward, define your causal horizon, the boundaries of your interaction with the universe. The light cone isn't just a diagram, It's a map of what's physically possible. It tells you where cause and effect can flow, what parts of the cosmos are connected to you, and which ones are forever beyond reach. The edges of the cone, the paths that light itself takes, represent the ultimate boundary of connection, the frontier where space and time meet in perfect balance. To make this analogy more intuitive, picture space-time as a three-dimensional grid stretching infinitely in all directions. Each point on that grid represents both a place and a moment in time. Now imagine shining a flashlight at that single point. The beam spreads outward, forming a glowing sphere that expands as time passes. If you were to trace that expanding sphere through time, it would form a cone shape, narrow at the point where the flash began and widening as light travels outward. That's the future light cone. Every possible ray of light emitted from that moment lies on its surface, marking the fastest possible way information can spread. Anything slower than light, a person walking, a signal traveling through wires, even a rocket hurtling through space, would move within the cone, never crossing its edge. This visualization also reveals why faster than light travel or communication creates paradoxes. If you could somehow send a signal outside your light cone, beyond that fixed boundary, you would, in some reference frames, be sending information backward in time. One observer might see your signal arriving before it was sent, flipping cause and effect. The universe, with its strict adherence to C, prevents that chaos. By ensuring that nothing can move outside the cone, space-time preserves a consistent order, where causes lead to effects and not the other way around. The light cone doesn't just describe what you can or can't influence. It defines your experience of reality. Every moment you live is a new point on your world line, and at each point, your light cone determines your potential future, what you could touch, see, or affect, and your accessible past, what could have reached you. The shape of that cone and its constant angle is the same for everyone, everywhere, because it's determined by the speed of light. What differs is how your world line moves through space-time. A stationary person's cone points straight upward in time, while a fast-moving traveler's cone tilts, yet both are bounded by the same limit. This is why physicists say that c is not just the speed of light, but the speed of causality. It's the defining slope of the light cone, the universal measure of how far something can influence something else in a given amount of time. The structure of space-time itself enforces that slope. If the speed of light were higher, the cones would be wider, and cause and effect would spread faster. If it were lower, the cones would narrow, and the universe would be more local, with fewer connections between distant events. But in our universe, C strikes a perfect balance, wide enough for galaxies to communicate with light, but limited enough to keep time flowing in one direction. You can think of it almost like a rule in a grand cosmic game. Every player, every particle, planet, and photon moves according to its own momentum and energy, but all must stay within the boundary of the cone drawn by C. No shortcuts exist. The light cone keeps the universe consistent and causal. It defines not just the speed of light, but the architecture of possible events. And yet, this structure does something even more beautiful than merely set limits. It connects everything that exists. Every atom, every star, every thought that has ever occurred lies within the web of intersecting light cones, each touching and influencing others through the steady propagation of information at light speed. In a way, light cones form the skeleton of spacetime's geometry, the framework through which all interactions happen. So, when we say that spacetime can be pictured as a grid, and light always moves along lines at a fixed angle through it, we're describing the universe's most fundamental geometry. The angle of that line, defined by the constant c, marks the boundary between possible influence and eternal separation. Inside the cone lies everything that can exist in causal connection. Outside, it lies everything that never can. This vision transforms light from being merely a fast traveler into something far more profound. Light defines the horizon of what is knowable, what is reachable, and what is real. It's the geometric heartbeat of space-time, the rhythm that structures causality, time, and existence itself. And now that we've seen how light's motion defines the boundaries of influence and order in the universe, it's time to ask a deeper question. If light defines the ultimate limit of causality, why can nothing else surpass it? What happens, physically and fundamentally, when anything with mass tries to approach that sacred speed? And why is reaching it forever out of reach? The universe is full of motion, from the spin of electrons to the rotation of galaxies. But there's one boundary that nothing with mass can ever cross: the speed of light. This limit isn't a suggestion or a technological obstacle. It's a built-in rule of reality, one that emerges directly from the structure of space-time. The closer anything with mass tries to move to light speed, the more stubbornly nature resists. Every bit of acceleration requires more and more energy. And if you were to try to push an object all the way to the speed of light, the energy you'd need wouldn't just be enormous, it would be infinite. That impossibility is what keeps every particle, planet, and spacecraft forever below light's pace. To see why, we have to think about what happens when something moves faster and faster. In our everyday world, adding energy is straightforward. You step on the gas pedal, the car goes faster. But once you approach relativistic speeds, those close to c, this relationship begins to change dramatically. Einstein's special theory of relativity showed that as an object moves through space-time, its energy and its inertia grow together. The faster it moves, the harder it becomes to make it go any faster still. It's not that its literal mass increases in the everyday sense, but its resistance to acceleration, what physicists call its relativistic mass, grows without bound. Imagine pushing a sled across ice. At first, it slides easily, but as you push harder, it gets heavier and heavier, not because you're piling more snow on it, but because space and time themselves are changing how momentum works. You pour in more and more energy, but less and less of that energy turns into extra speed. Instead, it goes into increasing the object's inertia, its tendency to resist motion changes. In effect, you're pushing against space-time itself, and space-time refuses to let you pass that ultimate limit. The math behind this reveals something striking. To accelerate even a tiny particle with mass, say a single proton, to the speed of light, you'd need an infinite amount of energy. Every increase in speed demands a disproportionate increase in energy, and as you approach c, that requirement explodes toward infinity. You could build a machine larger than galaxies, feed it the energy of countless suns, and still never get that proton to reach light speed. Nature's accounting is mercilessly precise. You can approach c, but you can never reach it. This rule explains why light, which is massless, is unique. Because it has no rest mass, it doesn't need energy to reach the speed of light. It's born there. It isn't accelerated to that speed. It exists at that speed. Every photon that has ever been emitted anywhere in the universe travels at c from the moment of its birth until the moment it's absorbed. For light, there's no concept of speeding up or slowing down. For matter, there's only the endless, unattainable chase. You might wonder what would happen if we tried to cheat this rule. What if we somehow gave a spaceship unlimited energy? What would it feel like as we pushed closer to light speed? The answer is both fascinating and paradoxical. From your own point of view inside the ship, no matter how much energy you pour into the engines, you'd never notice yourself reaching c. You'd keep feeling the ship accelerate. You'd see stars blur and space stretch, but you'd never actually see your own speed exceed the cosmic limit. To an outside observer watching from Earth, however, something different would be happening. As your ship accelerated, it would appear to require exponentially more energy for each small gain in speed. Its time would slow down relative to Earth, its length along the direction of motion would contract, and the energy you were expending would increasingly go into these distortions rather than into motion. If you somehow kept pushing, time on your ship would nearly stop compared to time on Earth. From your perspective, the universe outside would seem to rush by faster and faster, while to outside observers, you would appear to slow down, frozen just shy of C, never quite reaching it. That symmetry, your time slowing as your energy rises, is the universe's way of enforcing the cosmic speed limit. This principle doesn't just apply to large objects or spacecraft, it governs the behavior of particles too. In particle accelerators like the Large Hadron Collider, scientists propel subatomic particles to speeds astonishingly close to the speed of light, 99.99999% of it, yet never all the way. The more energy the collider pumps in, the less additional speed it gets out. Instead, that energy increases the particle's momentum and its effective mass. It's as though the particles are racing up an infinitely steep hill. Each step forward demands exponentially more effort. At the top of that hill, where C resides, lies an insurmountable wall of infinite energy. And this isn't just a mathematical quirk, it's a consequence of the deep geometry of space-time. The laws of relativity tie energy, momentum, and velocity together in such a way that crossing the speed of light would make them imaginary, no longer physically meaningful. The equations that describe the universe would cease to make sense. In other words, trying to exceed C doesn't just require impossible energy, it would push you out of the realm of reality as we understand it. What's beautiful about this constraint is how it keeps the universe consistent and logical. The cosmic speed limit ensures that cause always precedes effect. It keeps signals from arriving before they're sent and preserves the structure of time itself. Without this restriction, paradoxes would erupt everywhere. Events could influence their own causes. Information could loop infinitely, and the flow of time would lose all meaning. By placing an infinite energy barrier at C, the universe guarantees that everything within it unfolds in an orderly, causal way. So, while it might sound limiting, this rule is also what makes existence coherent. It's the reason we can trust the sequence of events, the reason we can send messages and expect them to arrive after they're sent, not before. It's a law that doesn't just govern motion, it governs meaning. And yet, light, free from mass, unburdened by inertia, glides effortlessly along this boundary. It is not hindered by time dilation or length contraction in the way matter is. It doesn't strive to reach the cosmic limit. It simply is the limit. Understanding why that is, why light is the one thing allowed to move at this ultimate speed, reveals even more about the elegant balance the universe has struck between energy, mass, and motion. The reason light can travel at the ultimate cosmic speed while everything else falls short isn't because it's stronger or faster in the traditional sense, it's because light is massless. This one fact changes everything. It means light doesn't need to be pushed to move. It doesn't require energy to accelerate to its speed. In fact, it never accelerates at all. It's born moving at the speed of light, from the instant of its creation to the instant of its absorption. You can think of it this way. For objects that have mass, the universe places a kind of energetic drag on their motion. To move faster, they need more energy because their mass gives them inertia, a natural resistance to changes in motion. The greater the mass, the greater the resistance. That's why pushing a car requires more effort than pushing a bicycle, and why pushing a planet is utterly impossible. This resistance becomes infinitely strong as an object approaches the speed of light. In other words, mass is what ties things to space-time, preventing them from skimming along its surface at sea. Light, however, has no such burden. A photon, the quantum of light, has zero rest mass. It doesn't sit still in space-time in any meaningful way, so it doesn't need to overcome inertia to move. Its very nature as a ripple in the electromagnetic field makes it something that can only exist in motion. You could no more stop a photon than you could freeze a vibration mid-wave without destroying it completely. For light, motion isn't a state to be achieved. It's a condition for existence. If you were somehow able to observe the universe from light's perspective, which, strictly speaking, isn't possible, things would look astonishingly different. For light, time wouldn't flow. The moment a photon is emitted, say, from a distant star, and the moment it's absorbed, perhaps in your eye billions of years later, are, from the photon's point of view, the same instant. No time elapses between those two events. In its own frame, there's no journey at all. The emission and the absorption happen together. Space and time collapse into a single, instantaneous connection. This is what makes light so special. Because it has no mass, it doesn't experience the normal exchange between time and space that massive objects do. When you move faster, your time slows down and your space contracts. For light, that trade-off goes to the extreme. All of its motion is through space and none through time. It doesn't age. It doesn't experience duration. It exists as a kind of eternal now, a messenger bridging two moments in space-time that, for it, are one and the same. This property also explains why you can't have slow light in a vacuum. You can't take a photon and dial down its speed to half or a quarter of c. Light speed isn't something you can adjust. It's baked into its identity. The moment light slows down, it ceases to be light as we understand it. The only way for electromagnetic radiation to move slower than c is when it's interacting with matter, such as in glass or water. But even then, what's happening isn't a true reduction in speed. The individual photons are still moving at c between interactions. They're just constantly absorbed and re-emitted, giving the appearance of slower travel. This subtle distinction, that light doesn't accelerate to its speed, but exists at it, is one of the most profound truths in physics. Every massive object lives within space-time, moving along paths that are curved, slowed, and bound by inertia. But light lives on the fabric of space-time itself, skating along its very edge. It's not trapped by the geometry of space-time the way matter is. Instead, it defines that geometry. The speed of light, c, isn't simply the velocity of photons. It's the metric that links distance and time, the fundamental ratio that determines how space-time itself is shaped. It's worth realizing how deeply this distinction permeates everything we know. When energy is converted into light, as happens in the heart of a star, the process doesn't push photons into motion. The energy of the reaction creates them already traveling at c, because that's the only way light can exist. When they are later absorbed, their journey ends abruptly, not because they slow down, but because their existence as light ends at that instant. This is also why photons, despite having no mass, still carry momentum. They may be massless, but they carry energy, and energy and momentum are two sides of the same physical coin. When light strikes an object, it can exert pressure, what we call radiation pressure. This happens because photons, though weightless, still possess the ability to transfer energy and momentum. This is how sunlight can push the tails of comets, how solar sails could one day propel spacecraft, and how even distant starlight gently nudges cosmic dust across the void. The idea that light is massless but energetic perfectly complements Einstein's most famous equation, E equals mc squared. Here, c squared acts as the bridge between energy and mass. It tells us that even a small amount of mass contains an immense amount of energy, and conversely, that pure energy, like light, can act as though it has mass when interacting with matter. Light is energy in transit, a ripple of the electromagnetic field, forever in motion, forever at the same universal pace. When you think about it, this distinction between light and matter captures something deeply poetic about the universe. Matter is what happens when energy is confined, bound to a point in space-time, weighed down by mass, slowed by inertia. Light is what happens when energy is free, unchained from mass, moving effortlessly through space-time at the only speed it can. Matter ages, light does not. Matter occupies moments, light connects them. Matter traces curves through space-time. Light draws the straightest possible lines. This is why, in many ways, light is not just another phenomenon within the universe. It's the universe revealing its underlying nature. It's the purest expression of space-time geometry in motion. The fact that light always moves at c isn't a coincidence or a limitation. It's the universe's way of expressing the relationship between space and time, energy and mass, motion and existence. And while light always travels at the same speed in a vacuum, it can appear to slow down in certain materials like glass or water. Understanding why that happens and why it doesn't violate the universal constant CE brings us to the next key point: the question of mediums and how light interacts with them without ever truly breaking its perfect rhythm. When we talk about the speed of light, there's an important detail that often confuses people. We say light always travels at the same ultimate speed, c in a vacuum. But then we also say that light slows down in materials like glass, air, or water. How can both of those things be true? If light is supposed to be the fastest thing in the universe, how can it slow down when it enters a denser medium? Is it breaking its own rule? The answer lies in understanding what's really happening as light moves through matter. The key is that light doesn't simply glide through a solid or liquid the way it moves through empty space. Instead, it interacts with the atoms and molecules that make up that material. And those interactions create the illusion of slowing down. The fundamental speed of light, the true cosmic constant, c, never changes. What changes is the path light takes as it weaves through a crowd of atoms. To see this clearly, imagine a photon, a quantum of light, entering a pane of glass. At the atomic level, glass is made up of a dense array of atoms, each surrounded by clouds of electrons. When the incoming photon encounters those electrons, it doesn't plow straight through them. Instead, it briefly interacts with them. It's absorbed by one atom and then re-emitted a moment later, often in the same direction. This happens countless times in the blink of an eye, as the photon's energy is passed from one atom to another like a baton in an ultra-fast relay race. Between these interactions, the photon is still traveling at the same speed it always does, c. But because of all those tiny pauses and detours, the average speed at which light's energy moves through the material appears slower. You can think of it like traffic on a busy highway. The cars, representing photons, can move at full speed between red lights, but every time they stop at an intersection, their overall progress slows down. The speed limit hasn't changed, but the journey takes longer because of those interruptions. In the same way, light's path through glass or water involves countless microscopic red lights, interactions with atoms that delay its overall progress, even though it never actually breaks its own universal speed limit. This phenomenon is what we describe with the index of refraction. a measure of how much a material slows light's apparent speed. Air, being relatively sparse, has an index of refraction just barely above 1, so light slows only slightly as it passes through it. Water, which is denser, has an index around 1.3, meaning light moves roughly 1/3 slower in appearance. Glass, depending on its composition, has an index of about 1.5, so light's apparent speed is reduced even more. But again, these slowdowns are not changes in the actual speed of the photons between interactions. They're a product of the zigzagging, stop-and-go motion that light undergoes as it's absorbed, re-emitted, and scattered by the material's atoms. Interestingly, this behavior also explains refraction, the bending of light when it passes from one medium into another. Because light's progress through different substances is slowed by varying amounts, the wavefronts of light entering a new medium change direction. It's like a line of marching soldiers stepping from pavement onto mud. The soldiers hitting the mud first slow down, causing the whole line to turn. In the same way, light bends when it moves from air into water or from water into glass, because its wavefronts experience different effective speeds on entry. What's remarkable about this is that even though light's apparent speed changes, the underlying physics remains consistent with Einstein's relativity. The universal constant c, the true speed of light in a vacuum, is still the foundation upon which all these effects rest. The interactions that cause light to appear slower don't violate that constant. They merely reflect how light's journey is mediated by the medium it's passing through. In fact, the index of refraction itself can be calculated from the electromagnetic properties of the material, its electric permittivity and magnetic permeability, just as Maxwell's equations predicted the speed of light in a vacuum. Once again, the connection between light and the fabric of space emerges. The material's internal electromagnetic structure determines how light moves within it. There's another fascinating twist to this story. In some special materials, under specific conditions, light can appear to move much slower, even as slow as a few meters per second, without breaking any laws of physics. Scientists have achieved this in ultra-cold atomic gases, where the interactions between light and matter are so finely tuned that photons seem to crawl through the medium. But here again, it's not that light itself is slowing down. Rather, its energy is being temporarily stored and passed along within the atoms, like a whisper moving through a line of people. The underlying constant, c, remains untouched. In fact, experiments like these beautifully illustrate the distinction between light's true speed and its effective speed. The true speed is absolute, a property of the vacuum, unchanging and universal. The effective speed depends on context, on how light's journey is shaped by the environment it moves through. When light escapes a dense medium and re-enters a vacuum, it instantly resumes its full cosmic pace, as though the detour never happened. No energy is lost in speeding up. No acceleration occurs. It simply returns to the natural state it never stopped having between interactions. This understanding clears up one of the biggest misconceptions about light and its speed. Many people imagine that light slows down because the vacuum somehow gives it less resistance, while denser materials hold it back. But the opposite is true. Light doesn't experience resistance the way matter does. It's the structure of matter itself, its ability to absorb and re-emit electromagnetic energy, that delays light's progress. The light isn't slowed by friction, it's slowed by conversation, a constant exchange of energy between photons and atoms. What's most profound is that even these apparent slowdowns reaffirm the primacy of C. Whether light is zipping through interstellar space, gliding through the air, or filtering through a pane of glass, it always adheres to the same universal principle. The vacuum defines the ultimate limit, the maximum speed information or energy can travel, and every other speed we measure is relative to that cosmic benchmark. So when we say light slows down in water, what we really mean is that the path it takes becomes more intricate, full of detours and brief pauses as it dances with atoms along the way. Its true rhythm, however, the universal tempo set by the geometry of spacetime, never falters. Even as light weaves through the densest matter, it carries within it the echo of that perfect constancy, that eternal C that defines the order and harmony of the universe itself. And now that we've seen how even the seeming variations in light's motion reveal the constancy of C, we can turn back to the grander picture, to the realization that this constant speed doesn't just describe how light moves, but how reality itself is structured. The value of C isn't just about photons, it's about the deep relationship that links space, time, energy, and mass into a single, coherent system, the framework that defines existence itself. Even after everything we've discussed, light slowing in glass, bending in water, interacting with matter, one truth stands untouched, unbroken, and absolute: the fundamental speed limit of the universe. C remains the same. No matter what happens to light as it moves through air, water, or diamond, no matter how gravity stretches space or how fast an observer moves, that constant value, the speed of light in a vacuum, never changes. It's the ultimate anchor of the cosmos, the unshakable reference against which all motion, time, and distance are measured. When we talk about C, we're not really talking about how fast light travels, not just in the sense of distance divided by time. We're talking about the structure of reality itself. C is the stitching in the cosmic fabric, the rule that connects how space and time transform, how energy and mass relate, and how cause leads to effect. It's the most fundamental constant in physics, not because light happens to obey it, but because everything else does too. Think about that for a moment. The value of C, about 300 million meters per second, isn't a number that was discovered by chance. It wasn't measured and then declared sacred. It defines the relationship between space and time. The meter itself, the unit we use to measure distance, is defined in terms of C. It is the distance light travels in 1 divided by 299,792,458 seconds. That means the universe doesn't measure light against our rulers. We measure our rulers against light. What makes this even more fascinating is that C appears not only in equations about light or electromagnetism, but in nearly every major law of nature. It's woven through Einstein's E equals mc squared, linking energy and mass through geometry. It's embedded in the equations that describe gravity, space-time curvature, and even the behavior of subatomic particles. C is the conversion factor between space and time, energy and matter, cause and effect. If the value of C were even slightly different, the entire structure of the universe would change, from how atoms hold together to how stars burn to how time itself unfolds. This constancy is why physicists say C is not just the speed of light, it's the speed of causality. It's the fastest possible rate at which information can travel, the maximum slope on the space-time grid. Any signal, any interaction, any force that attempts to move faster would fall outside the universe's causal structure, effectively breaking the chain of events that connects cause to effect. The constant C is what keeps reality logically consistent. It ensures that what happens now can only influence what lies inside its future light cone, that nothing in the universe can leap ahead of time to change what has already been. Even when light appears to slow down in a material, it never violates this rule. Those delays are only illusions of interaction. The photons are still traveling at C between atomic encounters. The interruptions only make their average progress appear slower. But the underlying rhythm, the pulse of space-time, never wavers. Every interaction, every exchange of energy between light and matter happens within the same immutable framework defined by C. This constancy also extends to the universe's most extreme realms. Even near black holes, those titanic wells of gravity that bend space-time almost to breaking, C remains the same locally. The curvature of space-time changes how light moves and how time flows, but the local laws of physics still obey that constant. If you were hovering safely far from a black hole, watching light curve around its edge, you might see that light appear to slow down, even freeze. But if you could ride alongside that light beam in its local frame, you would still measure it moving at C. The constancy of C holds everywhere. In the emptiest void between galaxies and in the densest depths of gravitational collapse. It's astonishing to realize that this single constant underlies all measurements of motion and all definitions of time. Every clock, every ruler, every physical process in the universe is tied to C. When you measure the distance between two stars, you're ultimately describing how far light travels in a given span of time. When you measure time, you're describing how long it takes light to cross a specific distance. C bridges those two measures, turning them into different aspects of the same reality. It's the conversion factor that makes the geometry of spacetime coherent. Because of this, C doesn't merely exist within the universe. It's what gives the universe its form. It defines the shape of spacetime, the flow of causality, and the relationship between energy and mass. It's like the tension in a vast cosmic web. Change the tension even slightly, and the web's structure collapses. If C were slower, the universe would look entirely different. Stars would burn out more quickly, gravity would act differently, and the very chemistry of life might not be possible. If C were faster, causality itself might break down, and the structure of time might lose its meaning. The value of C isn't arbitrary. It's precisely tuned to make a universe like ours stable, coherent, and alive. There's something almost poetic about this. C is a constant, yes, but it's also a principle, a universal rule that defines what motion and time even are. Light simply reveals that rule to us. The photon, massless and eternal, travels not because it wants to, or because it's powered by anything external, but because the geometry of reality compels it to. It's as if light is tracing the fundamental structure of existence itself, moving along the very lines that space-time draws. So when physicists say that C defines the structure of reality, they mean that everything we experience, time passing, distances separating, events unfolding, is anchored by that single value. It's not merely a feature of light, it's a feature of the universe. It's what allows equations to stay consistent, what gives meaning to motion, and what guarantees that every observer, no matter how they move, experiences a coherent version of reality. Even when light bends, slows, or changes color as it passes through different materials, it's still dancing to the same universal rhythm, the rhythm of C. That rhythm dictates the beat of every clock, the orbit of every planet, the pulse of every star. It's the law beneath all laws, the rule that holds even when all else changes, and that realization takes us to a deeper truth still, one that ties everything we've discussed together. Because C doesn't just set the limit of how fast things can move, it also defines how the universe measures everything, how space becomes time, how energy becomes mass, how reality keeps itself balanced. C is more than a speed. It's the fabric of relationship between all fundamental quantities. Understanding that brings us to the heart of the mystery, the breathtaking idea that the speed of light isn't just about how fast something moves through space. It's about how the universe itself keeps harmony between its dimensions, linking space, time, energy, and mass into one perfectly balanced whole. When we look closely at the constant c, we begin to see that it's not just a speed, it's a fundamental rule of measurement, the universe's way of defining how everything relates. C isn't about how fast light moves through space. It's about how space and time themselves are measured. It's the conversion factor that allows the cosmos to translate one into the other, turning seconds into meters, energy into mass, and motion into time. It is the universal yardstick by which reality keeps itself consistent. In the equations of physics, c is everywhere, not because light is special, but because it represents the deep relationship between all the basic quantities of existence. In Einstein's equation, E equals mc squared. C squared converts mass into energy. In relativity, c converts time into space and space into time. In electromagnetism, c defines how electric and magnetic fields weave together to form light. It is the thread that stitches all these seemingly different aspects of reality into a single, harmonious whole. Think of c as the universe's built-in exchange rate. If time and space are different currencies, c is what lets one be converted into the other without anything breaking. It ensures that when something changes in one domain, like an object moving faster through space, the corresponding change in time keeps the total balance intact. Without c, the laws of motion, energy, and causality would fall apart, because nothing would connect their scales. And what makes this so elegant is that c is not a property of light itself, but of the universe's geometry. It's written into the very equations that describe how space-time behaves. It's not something we measure, it's something we use to measure everything else. Every distance you've ever walked, every second that's ever ticked, every interaction between particles, all are governed by this one constant that keeps the cosmos coherent and predictable. So when we say the speed of light, what we're really naming is the universe's most fundamental rhythm, the steady, unchanging beat that keeps space, time, energy, and mass in perfect sync. It's the hidden symmetry behind every law of physics, the reason reality doesn't dissolve into chaos, but instead flows with structure and meaning. The beauty of the constant c isn't confined to abstract physics or the depths of the cosmos. It's woven into our everyday lives in ways most people never notice. This cosmic speed limit underlies everything from how satellites navigate our planet to how your phone connects to the internet. The same rule that governs the structure of space-time is, quite literally, keeping you from getting lost on your way to work. Take GPS, for example, one of the clearest demonstrations of relativity in action. The global positioning system depends on signals sent from satellites orbiting Earth, each carrying an atomic clock that ticks with astonishing precision. But those satellites are moving thousands of kilometers per hour relative to you on the ground, and they're farther from Earth's gravity. According to Einstein's relativity, both of those facts affect time. Motion slows it down, special relativity, and weaker gravity speeds it up, general relativity. The result? A clock on a GPS satellite runs slightly faster than one on Earth, by about 38 microseconds per day. That might not sound like much, but if engineers ignored it, the positioning data would drift by several kilometers every day. GPS only works because scientists account for c and the relativistic effects it causes. The system continuously corrects for the differences in time between the satellite's clocks and those on Earth, ensuring that the signals, traveling at light speed, can triangulate your location with pinpoint accuracy. Without c, there would be no navigation, no synchronization, no reliable digital map of our world. The same principle of light's constancy governs how information moves, whether across continents or through the circuits of your computer. Every time you send a message, stream a video, or browse the web, the data you're accessing is traveling at, or near, the speed of light. Fiber optic cables, the veins of our digital civilization, transmit pulses of light that carry bits of information. Even here, the effects of light's interactions with the medium show up. Those photons move slightly slower in glass fibers than they would in a vacuum, just as we discussed earlier. Engineers have to account for that delay when designing global communication networks. Inside your computer or smartphone, the situation becomes even more striking. The speed of light limits how quickly signals can move through circuits. When engineers design microprocessors, they can't just make transistors infinitely small or fast. They must consider the time it takes for electrical signals, which move at a fraction of c, to travel between components. In the tiniest chips, the physical separation of transistors is now so small that communication delays caused by light speed limits have become one of the greatest challenges in computer engineering. In a sense, every modern processor is a tiny race against the universe's ultimate constant. Even timekeeping itself, something as seemingly simple as telling time, depends on c. The world's most accurate clocks, atomic clocks, measure time based on the oscillations of atoms, which rely on electromagnetic interactions governed by the same laws that define the speed of light. These clocks can detect time dilation, the slowing of time, when moved just a few meters higher in altitude. Elevate a clock and it ticks ever so slightly faster because it's farther from Earth's gravity, exactly as Einstein predicted. The precision of these clocks, grounded in the constancy of c, makes technologies like GPS, global communication, and even international finance possible. C also defines the limits of information flow. No signal, not even one carried by light, can transmit information faster than the universal limit. This isn't just a technical issue, it's a cosmic law. It's what ensures causality remains intact across the universe. In communication systems, this translates into a hard boundary. Even in an ideal fiber optic network, messages between continents have unavoidable delays, not because of inefficiency, but because of the finite, immutable pace set by light itself. That's why messages between Earth and Mars take minutes to arrive, even when sent at light speed, a delay that future astronauts will have to live with. This same principle governs astronomy and cosmology too. When we observe distant stars and galaxies, we're seeing them not as they are now, but as they were when their light began its journey, sometimes billions of years ago. C defines not just how fast light moves, but how far back in time we can see. It's the speed of information from the past, bringing us the history of the cosmos one photon at a time. Perhaps most profoundly, C also sets the boundary for future technology. Physicists and engineers dream of faster-than-light communication or warp drives, but these ideas always run up against the same universal wall. No information, no matter how cleverly encoded, can outrun light without breaking causality. Quantum physics adds fascinating wrinkles to this, like entanglement, which seems to link particles instantaneously. But even there, no usable information moves faster than c. The universe's rule holds firm. So when you check your phone for directions, stream a live video from the other side of the world, or gaze at starlight that's traveled millions of years, you're participating in a cosmic dance, choreographed by c. Every signal, every transmission, every calculation and clock tick in human civilization traces back to the same universal rhythm that governs the motion of galaxies. The speed of light, then, isn't a relic of theoretical physics. It's the pulse that keeps modern life synchronized. It's the cosmic constant that enables the practical miracles of the 21st century, while quietly reminding us that even in our technological age, we are still bound by the same elegant, unyielding rules that govern the stars. And that brings us to one of the most tantalizing questions of all, one that science fiction loves to ask, and that physics answers with awe-inspiring precision. What if we could go faster than light? What if we could somehow break the ultimate limit set by c? Would the universe allow it? Or would reality itself begin to unravel? The dream of faster-than-light travel has always captured human imagination. Science fiction is full of warp drives, hyperspace jumps, and mysterious particles that move faster than light, shortcuts through the vastness of the cosmos. The idea is intoxicating. What if we could break free of the universe's ultimate limit, reach distant stars in moments, and outpace the light itself? But as beautiful as that dream is, physics tells us something sobering. If we could travel faster than light, the logical structure of the universe would collapse. Cause and effect would lose their meaning. Here's why. In Einstein's spacetime, the speed of light doesn't just define how fast things move, it defines what order events can happen in. Inside your light cone, causes lead to effects. You flip a switch and a light turns on. But if something could move faster than light, it could cross outside that cone, where time and space trade places. In some reference frames, the signal would appear to move backward in time. That means an effect could happen before its cause. A paradox that breaks the most fundamental rule of reality, that the past influences the future, not the other way around. Physicists have explored the idea mathematically. Hypothetical particles called tachyons, for example, are imagined to always travel faster than light. But their existence would lead to absurd consequences. They could carry information to the past, allowing messages to be received before they were sent. In some frames of reference, two observers could disagree about which event happened first, and both would be correct within their own physics. That's not just strange. It's impossible in a consistent universe. Warp drives and wormholes, popular in science fiction, flirt with the same boundary. Some speculative models, like the Alcubierre drive, suggest you could compress space ahead of a ship and expand it behind, letting the ship ride a wave of distorted space-time without technically breaking the light speed limit locally. But even those ideas demand enormous, likely impossible amounts of energy, and would still risk tearing causality apart if used to move faster than light overall. In essence, faster than light travel doesn't just break a rule, it breaks reality's logic. It lets you send a signal to your own past, creating the classic grandfather paradox. What happens if you go back and prevent yourself from existing? The universe seems to protect itself from such contradictions by making c unbreakable. The speed of light isn't just a limit of motion, it's a safeguard of order. So while it's thrilling to dream of bending space and racing past light's beams, doing so would mean rewriting the fundamental script of the cosmos. The universe's consistency, its causal fabric, and even our understanding of time depend on that sacred boundary. And maybe that's why the limit exists. Not to constrain us, but to preserve the harmony that lets existence make sense at all. In the end, the speed of light's limit isn't a restriction, it's a revelation. It's not some arbitrary cosmic speed cap imposed to frustrate our ambitions of crossing the stars. It's the universe's way of defining what motion, time, and reality actually are. It's not a barrier, but a blueprint, the rule that gives meaning to movement and structure to existence. When you think about it, the fact that there is a universal limit tells us something profound. The cosmos isn't chaos. It's not an uncontrolled storm of events moving at random speeds and directions. It's a coherent system bound together by a simple principle, that there is a maximum pace at which cause can reach effect, information can travel, and reality can unfold. That principle, embodied in c, ensures that the universe remains consistent and comprehensible. It's the reason time flows in one direction, the reason we can measure distance, and the reason we can trust the connection between action and consequence. Light's speed is the universe's heartbeat, steady, eternal, unchanging. It's the rhythm that synchronizes everything, from the flicker of atoms to the motion of galaxies. Without that rhythm, space and time wouldn't have meaning. They would be disconnected, chaotic, and without structure. C is the harmony that keeps them in tune, the mathematical thread that binds existence into a single, unfolding whole. And yet, there's something wonderfully poetic about this limit. Light, the thing that illuminates our world, that reveals all we can see, also defines the boundaries of what we can see and what we can never reach. Every sunrise, every reflection, every glimmer in the night sky is light tracing the edges of possibility, whispering the story of a universe that moves, always, at its own perfect pace. So when we look up at the stars, watching light that has traveled across billions of years, we are not just seeing across space, we're seeing across time, following the universe's own thread of continuity. That light, moving at C, connects us with the beginning of everything, bridging the gap between past and present, matter and energy, space and time. The speed of light, then, isn't merely about how fast something moves. It's about how the universe defines movement itself. It's the key that links existence to order, energy to form, and time to meaning. It is, in the truest sense, the pulse of reality, the constant that reminds us that even in a cosmos so vast and incomprehensible, there is structure, elegance, and unity. Light's speed limit isn't nature holding us back. It's nature holding everything together. It is the measure by which the universe knows itself, and through it, we glimpse not just the laws of physics, but the poetry of existence. The universe's speed limit is not a constraint. It is creation's signature. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.